Welcome to part 5 of this introduction to MR physics. This one deals with basic MR pulse sequences and also acceleration strategies. Just to recap, so if we put a million protons or hydrogen atoms in an external magnetic field, we're going to have 10 extra protons that are processing about the spin up state because they're at a slightly lower energy. They're going to be randomly oriented along this cone, meaning that we have no coherent magnetization in either X or Y, but we do have a coherent M0 magnetization that forms in the same direction as this B0 field. And what we do in MR imaging is we apply these shorter-lived B1 pulses that we apply in the transverse plane that I'm always showing in green here. The main magnetic field is in blue and the magnetization is typically in red. And so by applying these B1 fields, we can tip the magnetization by some portion into the transverse plane. Here I'm showing a flip angle of alpha. We know that after we turn off the magnetic field, we're going to get relaxation in the transverse plane and recovery back along the Z direction, according to T1 and T2. And this is illustrated by the Bloch equation, which basically just describes the temporal evolution of the magnetization over time. And then this first term really deals with this RF tipping that we just showed. So we know that the transverse magnetization that is fluctuating in the transverse plane is going to induce a current in a pickup coil that looks like this, and that's going to generate the signal that we measure. And this signal that we're collecting is essentially one line of K-space, okay? So this red blob here is sort of a pictorial representation of what this line of K-space actually looks like, okay? Last time we talked about the connection between this 2D K-space and 2D image space. So if we look at the image of the brain on the left, this is the corresponding K-space on the right, and we can transform back and forth between these two images by either applying an inverse Fourier transform in this direction or a forward Fourier transform in this direction. And just to remind you of the zones of K-space, the central portions of K-space represent the very low frequencies, remember from our sinusoids from last time. And so that represents the sort of bulk details in our image on the left here. And if we look at the opposite portion of K-space, basically everything except the middle, this is the higher frequency information, which basically forms the sharp edges in our image here. And right towards the end of last time, we talked about equation number 3, which is the K-space equation. And basically it just says that where we're located in K-space at any given time is given by the area under the curve of our 3D gradients. Okay, and so for example, if we look at these two gy and gx gradients as a function of time, so the first gy gradient moves us up a certain amount in K-space in the ky direction. We apply a negative gradient here in the gx direction, which moves us over here, and then we acquire our data as we move across in this positive double time lobe, okay? And so what we're going to do for this part 5 is talk about just basic MR pulse sequences and even talk about some image acceleration strategies that some of you are probably actually using, whether or not you even realize what you're actually what you're actually doing to the scanner when you press a certain checkbox. So what we're going to start with is we're actually going to take a step back and talk a little bit about NMR spectroscopy. So this has been around since the 1940s. This is what Bloch and Purcell really got their Nobel Prizes in chemistry and physics for. And so this is just a pictorial representation of what NMR spectroscopy is, and some people may be doing either sample spectroscopy or even in vivo spectroscopy. So imagine we have just a test tube or a very small cylinder of water that we place in our magnetic field. We know we're going to get that coherent thermodynamic equilibrium magnetization M0 that's going to point along the direction of this Z B0 field. So imagine we just apply a simple 90-degree pulse, and then we have our free induction decay, and we measure that. So what we can do is take this free induction decay and do the Fourier transform on it, and basically we would get a spectrum that looks like this. So basically in this case, the axis along the bottom here is frequency, and this is just signal intensity as a function of frequency. And so if we have a simple water cylinder, water is going to have a single resonant frequency that we know, and it's going to have basically a long T2, just like we had when we looked at CSF. CSF is mostly water. Water has a long T2, and we'd do this Fourier transform, and we would get something that looks like this. And so if we look at the actual properties of what these NMR spectra actually mean, there are certain things that we can learn about the substances themselves that we're actually trying to determine with our spectroscopy. So this is what it would look like for this particular T2 decay. So it looks something like this. Now, if we had a particular chemical species that had a shorter T2, what does that mean? What does having a shorter T2 actually mean? Well, it means that in the transverse plane, the spins are dephasing from each other faster than they did for the first species. And how that manifests itself on the NMR spectrum is that this peak actually gets broader. And you can kind of think about it this way. If you know that there's a very heterogeneous environment that the hydrogen protons in your sample are experiencing, you're going to get a bit more of what looks like a spread of individual frequencies that are centered around whatever your main omega 0 is. So the general rule of thumb is that the width of the half width of your pulse is inversely proportional to your T2. Okay? And the amplitude of this signal is going to depend on how many of those protons are actually present in your sample. And so what we do with NMR spectroscopy is we can actually determine what type of molecules are present within our sample, basically by looking, and in what quantities, based on how many peaks we see, what the widths that we see, and the actual amplitudes of those signals. And so let's go back to our example of just a simple cylinder of water. Well, we already know what that's going to look like when we look at the spectrum. It's really not that interesting. But what if we start taking a cylinder that has several chemical species? And you can tell on the slide that there are now several species because the cylinder has gone from blue to purple. And so basically each one of these chemical species are going to have their own unique free induction decay that's going to have a T2 component, and it's going to have a concentration based on how much of that particular compound is present in our sample. And so what is going to happen is those free induction decays are going to have constructive and destructive interference when we actually try to read them out on our pickup coil. And so applying the same rule, we apply this Fourier transform on this complicated decay, and basically we can get out the actual spectrum that describes, okay, so in this particular one that I've drawn here, we had 3 different species. This one has a very large peak, so there's a lot of it, and this one's got a much fatter peak, so that means that we know it's got a shorter T2 decay. Okay? And so basically what we do in spectroscopy is we build up a plot, basically, of the signal intensity as a function of center frequency. Okay? All right, so now we're going to take it a step further. So we're going to go back to our boring cylinder of water, and instead of just applying the 90-degree pulse and doing a readout, we're going to apply a gradient in the x direction. So now we've got faster dephasing of the signal in the transverse plane because we're applying this gradient across our sample. Okay, and just to remind you, if we're applying a gradient in the x direction like this, excuse me, what that means is that we're changing the Z component of the magnetic field as a function of X. And so if you think about our B0 field being this strong, then when we apply our X gradient, the spins would actually be experiencing something like this pink curve. And so now we're applying that across our cylinder. And so what sort of frequencies would we expect outside of the cylinder? Zero. There's nothing there. It's just air. Just like when you're imaging in the head, outside of the head where there's nothing, you get noise. Okay? So what we can do is basically think about now we've got a cylinder where the spins are precessing as a function of X. So this is our original omega 0 here in the middle, but because of our gradient, we have this linear ramp along the X direction of the spin precession. Okay, what does that actually look like when we start looking at it from the top? Okay, so this is the same plot that I just showed a second ago. Well, what that actually looks like when you're looking at it from the top is something like this. So we have the spins in the very center, all precessing with our original omega 0. These ones are precessing a little bit faster. These ones are precessing a little bit slower. And so if we did our same 90-degree readout that we just did and did our Fourier transform on it, we would get something that looks like this. Now remember, this is just a cylinder of water. So if we didn't have that gradient, we would just get a single sharp spike. Now, in this case, we actually get something that looks like this. Well, we can actually think about that instead of a function of frequency, we can actually think about it as a function of position. And so now we've just changed the axis. So instead of looking at the signal as a function of frequency, we're looking at it in terms of the actual X position of the spins. Okay, now why does it have this particular shape? Well, remember, the amplitude that we're seeing in our spectrum is related to concentration. Right? And so if we look at what the spins are doing from the top down again, remember, we had this gradient along the X direction. So right in the middle, we have the most spins that are precessing with omega 0, which is why the amplitude in the center is higher. And as we move in either direction, we have fewer and fewer and fewer of these spins at that particular frequency. And so that gives us this spectrum. Now, what we would actually call this in imaging is actually a projection. We are acquiring a 1D projection through image through this particular sample of water. And if we can acquire enough, so in this case we've gone from one cylinder to two cylinders, and we're applying a gradient in the we're basically doing our readout in the directions that you can see here, and we're building up a series of these spectra. Well, using radon back projection, or CT projection if you want to think about it that way, we can reconstruct an image. Has anybody seen these images before? Has anyone not seen these images? Raise your hand. These are the original first ever MR images that were created by Paul Lauterbur in his original paper. And yes, I mean that Paul Lauterbur, the one that won the Nobel Prize for Medicine in 2003. And so this was the first ever MR image. So he acquired 4 different projections that were 45 degrees apart, did a simple back projection reconstruction, and created this image of these capillary tubes that look just like this. Okay? Now, what we do typically in MR imaging is we don't actually do projection. We actually acquire a full 2D or 3D K-space and then do inverse Fourier transform on that to get our images. But basically what Lauterbur was essentially doing was acquiring 4 different lines through the center of K-space and then doing a radon transform to do the back projection reconstruction. Okay? Now, let's go back to our equation number 3 just to rehash some of the things that we're talking about. So if we think about the acquisition of a single line of K-space with a standard gradient echo with no fancy stuff going on, no diffusion, no spoiling, no nothing, it would look something like this. So we apply the phase encoding gradient at the same time as our readout dephaser. So that would move us from the center of k-space up to here according to this equation, because we were taking the area under the curve for both the gy and the gx into account at the time. And then we do a simple readout. And then what we do for a simple k-space trajectory for a gradient echo is we basically, every TR, play out a different amplitude of this gy gradient. And basically we build up this k-space in this manner, okay? And then once we have our full k-space, we do the inverse Fourier transform and we get our image. And then if we're doing multi-slice imaging, then we move to the next slice, repeat the same steps. Move to the next slice, repeat the same steps, okay? Now, what does a spin echo acquisition look like? So, if we want to, so in this particular example, I'm making sure that we're acquiring the k-space in the exact same order. So we're acquiring from left to right and top to bottom, okay? So remember, in spin echo, what we do is we apply our first, typically a 90-degree pulse. We have these dephasing gradients here, and then we apply a 180-degree pulse here and then read it out. Well, what that looks like in a k-space trajectory is that initially we would apply a negative gradient here and a positive gradient here that would actually move us down to here according to this equation. By applying that 180-degree pulse, we are flipping everything through the center of k-space. So that 180-degree pulse flips us to the opposite corner of k-space. So that moves us up here, and then we have the same readout that we would have in a gradient echo. But the key thing here is that in order to go up or down or left or right in k-space, we have to think about the fact that we have to do it in the opposite gradient sign before that 180-degree pulse compared to our gradient echo counterpart. And so just to show what a spin echo k-space trajectory, so this is just the same animation over here. Basically, we always have the same readout gradients here. We've got our 180-degree pulse in between here, and every TR we just change the amplitude of this gy gradient so that it moves us, in this case, further and further down in k-space or higher in k-space depending on the amplitude, and then that 180-degree pulse flips us to the opposite corner. All right, now I mentioned just a second ago the fact that we have to do this for multiple slices. So we're gonna focus most of our work here on assuming multi-slice 2D imaging instead of 3D imaging. Now I showed this diagram before. So say we know we want a particular anatomical slice in the Z direction, in this case the axial brain image that I'm showing here, and we know exactly where that's positioned within the head. So I showed this diagram before that we said, okay, well, we simply just tune our B1 frequency to that particular slice location and we're done, right? Well, there's a bit of a hiccup there, and that's the fact that we don't have infinitely thin slices. We actually prescribe, when we're sitting down at the magnet, we prescribe some slice thickness that we call delta Z in this particular case. And so because we want this slice thickness to happen while we have this GZ gradient on, what it means is that we actually have some corresponding slice frequency shift across that slice. And so that's going to have an impact. So what that means is that if we just apply the center frequency right here at this point, we're not going to be getting this full slice. And actually, it's a little more complicated than that. But basically, you can think about it that way. And so up until now, I've always shown the radio frequency pulse in all of these plots as this boxcar function that is also played out while this GZ gradient is on. And so this isn't just a simple boxcar. This is basically what we call the envelope function, because remember, we've got it oscillating in the transverse plane. You can just think about this as the shape of the general sinusoid. So if you see a square pulse, remember you still have that B1 that's rotating in the transverse plane, so it actually looks like it's oscillating like a sine wave. But what we actually want to do now is excite this this slice. Let's say half a centimeter or even a full centimeter in the slice direction. So what we really want is a slice profile that looks like this. So how would we possibly excite something in a frequency space based on something in a time space that looks like this? Well, this goes right back to what we talked about last time. We have this sinc function. And so basically now, instead of having this boxcar function, what we do is we modulate the amplitude of that sinusoid that's still bouncing back and forth at that frequency by this sinc function. And what that does is it allows us to excite only this particular slice of particular assigned width that we know. Okay? And so if we go back to our pulse sequence diagrams, we go from something that looks like this to something that looks like this. Okay? And all of our echo times and TRs are based relative to this center of this sync pulse. Okay? Now, there's one more tiny piece to our puzzle here on pulse sequence diagrams. So, as I said, we measure our echo time and our TE relative to where the maximum amplitude of our sync function is. Now, what happens is, because most of the magnetization is tipped into the transverse plane at the center of this pulse, which is why we measure TR and TE respective to that, we still have this GZ gradient on for this duration. So what is that going to do? Well, that's going to actually start dephasing the spins early. And so what we have to do is apply a second lobe in the selection that looks exactly like this. So it's exactly half of the area. And what that does is, after our alpha pulse and this little dephasing lobe here, we apply an equal area gradient here just to rephase everything so that we don't lose any signal. And some of the original papers actually talk about, it took them a while to figure this out. They were getting really, really poor signal in some of their images and spectra, and it was because they hadn't figured out to put this refocusing lobe here to basically give them back the signal that they were missing. Okay? And so now we finally have a full 2D gradient echo pulse sequence that looks something like this. So we have our sync pulse, alpha pulse here. We've got our slice selection gradient here with the refocusing lobe here. We've got our phasing coding that is going top to bottom here. And then we've got our dephasing GX gradient, and then our sampling positive gradient here. And then this is the signal that we read out. And then the corresponding spin echo sequence looks something like this. So again, you have your sync pulse here with your refocusing lobe. Remember, if we want to have the exact same K-space trajectory as our gradient echo, that we have to flip the sign of these gradients before the 180-degree pulse. Now, the other thing that you'll see here is the fact that there's no refocusing lobe here on the 180-degree pulse. Some of them do have different refocusing lobes, but for this example, we just have to think about the fact that this is the whole purpose of this 180-degree pulse is to rephase everything anyway. So we don't need to apply a rephasing gradient on this 180-degree pulse because that's what it's meant to do anyway. Okay? And then we have our readout that looks something like this. And so basically we go back to the different image contrasts that we had talked about several times now, our T1 weighted, T2 weighted, and proton density weighted images. And so basically by manipulating the echo time and the TR for both these spin echo sequences and gradient echo sequences, we can get different image contrast. Okay?